Hello and welcome to lecture 17. This is the second part on sequences, and then in the next part of this video I'm going to start talking about series. So we need to cover some vocabulary on sequences. So I have some definitions and terminology on the board that you should be familiar with, and we're going to go through these definitions first, and then I'm going to give you examples of sequences where we're going to use some of this vocabulary. So a sequence A sub n is increasing if the previous term A sub n is less than A sub n plus 1 for all n. So the previous one, n, the previous term, is going to be smaller than the next one, and that's always true. Then you're increasing. And if you're decreasing, the opposite's true. The previous term was always greater than the subsequent term for all n. And then we say a sequence A sub n is monotonic if either 1 or 2 is true. And all monotonic really means is that it moves, the sequence moves in one direction. So it's either going to move up, it's going to be increasing, or it's going to be strictly decreasing. So monotonic just means you move in one direction. I think I'll just write that too. So one direction. So being monotonic means you're either this or you're this, 1 or 2. To be bounded below, what that means is that there is a number, and we're going to just call it little m, such that little m is less than or equal to all the terms of the sequence for all n. So you can find some number, we'll call it little m, such that it's less than every single term in the sequence. And then for bounded above, it's very similar. There is a number, so call it some number, capital M, such that capital M is greater than or equal to each term in the sequence for all n. And this little m right here, we call this a lower bound. And then this capital M right here, we call this an upper bound. And I'm going to show you some examples in just a second where some of these are going to apply. And then if you're bounded, that means 4 and 5 are true. So notice the difference here. For number 3 to be true, only one of these have to be true. But if you're a bounded sequence, to be bounded means you have to be bounded up from above and below. OK, so here's the definitions. Let's apply it to some examples. So let's graph some of this sequence right here. So if you plug in 0, the starting index here, you get 0. If you plug in 1 for n, you get -1. If you plug in 2, you get -4. And then this continues on forever. So what I'm going to do is I'm going to graph what's going on, and I'll graph those first few terms as well. So I plugged in 0, and I got 0. And then I plugged in 1, 2, maybe I'll do 3 as well. And I'm just realizing I'm getting negative numbers. So maybe my graph should look more like this, where I'm kind of emphasizing down here more. So here's -1. So when n equals 1, we got -1. And then when n equals 2, you get -4. And these points make up the sequence. And as you plug in larger and larger numbers, so you say as n goes to infinity for this sequence right here, -n squared, what'll happen here? So the numbers are going to become more and more negative, and they're going to be larger and more negative. So this actually goes to -infinity. So this is a divergent sequence. Which of these vocabulary words does this apply to? So is this an increasing sequence? Is the previous term less than the next one? Actually, no. It's quite the opposite. It's a decreasing sequence, right? Decreasing means that the previous one is always greater. So we could say that this is decreasing because each of the following one is going to be less. Because it's decreasing, that means it's monotonic as well. And then bounded below means we can find a number that's going to be lower than all the terms. But that's going to be false because the sequence goes, it goes down here forever, and it goes down to negative infinity. So I'm never going to be able to find a number that's going to trap them all from below. However, there are numbers that I could pick. Like let's say I picked 0. For capital M equal to 0, I can basically put a roof on all the points on the graph, right? That's what it means to be bounded above. So M equals 0 in an example, that would show that this is bounded above. So we're bounded above. And I don't have to pick 0. I could pick any number that's larger than all of them. I could pick 1 or 2. And 0 is the lowest one I could pick. So we're bounded above. Because we're not bounded below, we're not bounded. So these 3 vocabulary words apply to this one. You might want to pause the video and try this one now, but I'm going to do it. So just like before, I'm going to plug in some numbers. If I start with 1, I get 2 over 1 is 2. And then if I plug in my next number, if I plug in 2, I get 3 over 2. And then maybe I'll do one more. So I'll plug in the next one. It's 4 over 3. This continues forever. I'll do the same kind of graph just like before. And I plugged in 1, 2, and 3. So if I plug in 1, I got 2. If I plug in 2, I got 3 halves, which is 1.5. If I plug in 3, I get 4 thirds, which is like 1.33. So this is what's happening. The limit as n goes to infinity for this sequence, I have the same powers. It's just 1, the ratio of the leading coefficients. So eventually, these dots are going to approach 1. So now let's look at this one. So first things first, is this decreasing or increasing? It is decreasing. 2 is the largest, and then all the points are going to be lower from then on. So this is also decreasing. So as a result, it's monotonic. So I have decreasing, I have monotonic. Are we bounded below? Is there a number that's strictly going to be below every single term in the sequence? Yes. It approaches 1, so 0 would be an example. If little m is 0, 0 would be below all of the terms. I could also pick 1 as well, but I'll just pick 0. So this means we're bounded below. Can I choose a capital M that would trap them all from above, like put a roof on all of them? Yes. If capital M is 2, then you trap all of the terms between 2 and 0. All the terms get trapped in there. This means we're bounded above because we found a number that goes above all the numbers. And then together, because we're bounded above and below, we just say that that's bounded. So 4, 5, and 6 are true for this one. OK, so that's just some terminology that's going to come up. I want you to know all those things and what they mean. Now I'm going to turn my attention to the monotone convergence theorem. And there's 3 different scenarios that I want you to know, like 3 different statements. So the first one is every bounded monotone sequence converges. The second one I'd like you to know is an increasing sequence bounded above converges. And then the other one is a decreasing sequence bounded below converges. So there's very specific adjectives you need. You need it to be bounded above and increasing, or you need to be bounded below and decreasing for your sequence to converge to something. And let's just look at the picture for that. So off to the side here for number 2, let's just draw something that's strictly increasing. Well, first I'm going to give myself a bound. Let's say you're bounded above by capital M. So that means none of the terms can go above this dotted line. And now if you have some kind of increasing sequence, and it can only be increasing, and it's increasing the whole time, eventually you're going to hit the ceiling, basically. If you say that you're trapped above and you're always going up, there's going to be some number that you hit. Maybe call it L. There's some number that you're eventually going to reach. And that's what the part of this theorem is saying. And then if you want to draw the same picture for this, let's say you're bounded below by this little m. And then you know you have a decreasing sequence. So it's doing something like this. And no matter what it's doing, the whole time it's decreasing. And eventually, it's going to be trapped by the floor right here. It's going to run into this. And then you're going to approach some L value. OK, so if you think about the pictures, this kind of makes sense. OK, so I just wanted to share that with you. Let's look at this last example where I can show you what a recursive sequence is. So this gives us an example of a recursive sequence. So we're going to define it in this way. So we're going to say the very first term of the sequence is 2. And then each subsequent term is given by the formula a sub n plus 1 equals 1/2 a sub n plus 6. Does this converge? So let's think about it. What you need for a recursive sequence is you need a situation where your general formula depends on one of the previous terms. So the formula itself is a part of its formula. That's what a recursive sequence is. So basically, each previous term, the a sub n term, gives you the next one. And as a result, you need them to give you the first term. You need to get started somehow, right? So we tell you that the first term is 2 here. And then if you follow this, let's say n equals 1. So if you plug in n equals 1 into here, you get the second term, because n is 1, equals 1/2. N is 1, so you get a sub 1 plus 6. But then that means that the second term is this first term, which was 2, plus 6, which is 8. And then it's 4. And then you take that 4 and you go and do another one. So now if n equals 2, we plug it into the formula here from the very beginning. So if you plug in 2, you get a sub 3 is 1/2. N is 2, so a sub 2 plus 6. So that means a sub 3 is 1/2. A sub 2 is 4, so plug that one in. We have 10. So this is 5. And you can see how this continues forever, right? OK, so this is the idea behind a recursive sequence. I'm going to try to convince you right now with kind of a loose argument here that a sub n plus 1, this sequence, is bounded above by 6. And let me just try to convince you of that right now just by kind of explaining. So the formula, the main formula is 1/2 of these two numbers. So you could think of this as it's an average formula. This is the average of two numbers. The first number is always 6 here. It's the average of 6, and then a new number you plug in. So we're always going to plug in a number less than 6. And the reason is, previously we plugged in a number less than 6. And if you take the average of a number that's less than 6 and 6, the average is always going to be less than 6. And then you're going to plug that in, and you get another average between a number less than 6 and 6. So that's my reasoning for why this is never going to be larger than 6. So I hope that makes sense. So now we're bounded above by 6. However, if you notice our terms here, so I had 2, and then I got 4, and then I got 5, we're always going to be increasing because the way averages work is if you take 6 and you average it with a number lower than 6, the 6 is going to help bring up the total average. So this is going to be an increasing. This will be increasing. So I can use the theorem, and I can say by the monotone convergence theorem, this sequence right here it converges. It has to, because it's increasing and it's bounded above by 6. Capital M here is 6. So I know it converges. Let's go ahead and figure out what it converges to. So let's take the limit as n goes to infinity of a sub n plus 1, which is equal to the limit as n goes to infinity. The formula for that is 1/2 a sub n plus 6. So if n goes to infinity, n plus 1 and n are both going to go to infinity. So these are both going to go to the same limit. So on the left, the limit of this sequence right here, a sub n plus 1, that's L. And over here, these constants are unaffected by the limit. So if I plug in infinity for n here, this is also going to go to L. So I get 1/2 L plus 6. So if you look at the left and the right, that just tells me L equals 1/2 L plus 6. And now I need to solve this. So multiply both sides by 2, subtract the L, and you get the limit of this sequence. It converges to 6. All right, so that's going to be it from me for sequences. After I come back, we're going to move on to something very different, and this is going to be called series. I'll see you soon. Welcome back. So now we're going to be talking about series, which is a completely different animal than sequences. In the first part of this video and in the last video, we talked about sequences, which are just lists of numbers in a specified order. Series are something totally different, which we're going to do now. And I'm going to warn you that the biggest area of confusion I see from students in this exam period is telling the difference between a sequence and a series. So you need to be certain you're dealing with one of those or the other things, because many of the theorems that you learn later get all mixed up if you confuse a sequence for a series. OK, so let's talk about what a series is. So an infinite series, what it does is it adds together all the terms of an infinite sequence. So you take whatever that list of number was, like all the numbers, and you add them all up. And the infinite series keeps track of the sum of all of them. And the way you write a series is like this. So you have the summation, capital sigma, from n equals 1 to infinity of a sub n. Or you can just write this, if you don't specify the indices, as just the summation of a sub n. So this a sub n was our formula for the sequence. But now what the summation means is you're going to take every single number in the list and add them all together. And that's what a series is. So let me do an example. We're going to take the summation from n equals 1 to infinity of 1 over 2 to the n. So what you do is you add together all of the numbers in the sequence. So if you plug in 1, the first thing you get for a sub n is 1/2. And then you just have to keep adding it together, like accumulate all of it. So if you plug in 2, you get a 4th. If you plug in 3, you get an 8th. And then this sum is equal to the sum of all of those numbers forever. You may know what that is. I'm not going to spoil it and say what it is, because we're going to do some examples soon. But this is what I mean when I say an infinite series, is you add up all the members of the sequence. So we're going to say S of n is going to denote something called the partial sum of a series. So for example, S of 1 is just the first term of the sequence. S of 2 is you take the first 2 members of the sequence and just add those 2. And then S of n would be a1 plus a2, and you'd go all the way up to the nth term of the sequence and just add those, and you'd stop. You wouldn't go forever. So for example, for this one right here, the one I was just doing, S of 1 is 1/2. S of 2 is the first term plus the second term, which is 1/2 plus a 4th. That's 3/4. And I could keep going like that. So that's just a concrete example of what a partial sum is. It's like you stop at a certain point. Then this next thing is very important. So if the limit as n goes to infinity of the partial sums, if that equals s and it exists, then the infinite sum is convergent. So if you figure out that the partial sums actually converge to a number, that is the sum of all the members of the sequence. So that's convergent. And then otherwise you say, and you can probably guess by now, otherwise it is divergent. It being the infinite sum. It is this. That's what it is talking about. I want to be specific. The infinite sum is divergent. So if the limit of the partial sums does not go to s. OK, so that's what an infinite series is. We encountered a special type of infinite sequence. And you're going to need to know this special type of infinite series as well. It's called a geometric series. So this is the sum of the geometric sequence that we learned before. So we start with a sequence like this, a sub n from n equals 1 to infinity. And it looked like this. You have a starting term a. And then from a, each time you multiply by some fixed r. So you multiply by r, and then you multiply by another r, dot, dot, dot. So that r was what you multiply by. And then it looks like this if you put it in infinite sum notation. It's a summation, n equals 1 to infinity, of a sub r to the n minus 1. And if I were to plug in my values for n, so if n equals 1 here, I get a r to the 0 is a. And it's a sum, so you add all these together. So this is n equals 1. If n equals 2, you get ar plus, and it continues. And it's that infinite sum right there. This is a very special type of series because you have that fixed r that's getting multiplied to each subsequent term. So this is a special type of series. And it turns out that this will converge if the absolute value of that r, the fixed r you're multiplying, is less than 1. And we have a formula for what it sums to. And this sum, n equals 1 to infinity of a to the r minus 1, that's equal to a over 1 minus r. And then I'm going to say if the absolute value of r is greater than or equal to 1, the sum diverges. OK, so one other thing I like to think about for this formula is instead of calling it a, I like to call it the first term. This helps alleviate a lot of the confusion I had when I was first learning this topic. So I'm going to show you what I mean by that. So you can remember this formula as a over 1 minus r, or you can remember it as first term over 1 minus r. Let's calculate this. So match it up with what the formula looks like. So you can see here, my a is 5. And then here, my r is given as 2 over 3. So the absolute value of r, it's the absolute value of 2 over 3. And that is less than 1. So we know that this converges. Because it converges, you can use the formula. You can't use the formula if it diverges. But it's going to converge. So you're going to use this formula. It's a over, so a is 5, over 1 minus, r is 2/3. And then I would get 5/3 over 1/3. So that's just flipping the 3 up, and it's 15. So this infinite sum right here converges to 15. If you wanted to write out the first few terms, you plug in 1, because that's where we start. If you plug in 1, you get 5. If you plug in 2, you get 5 times, and you get 2/3 plus, and then that would continue on forever. So what we're saying is that infinite addition here ends up adding to 15. All right, let's look at this next one. So this one looks a little more tricky. It's not exactly in the form you need it, where you have an r to an n minus 1 power. The powers are different. So you're going to have to be able to manipulate these first before you can use the formula. So I'm going to show you some algebra tricks. That's why I'm here. So I want these powers to match. I need to remove one of the 4s, because then when you remove one of these, the power will shift to what you need. So we're going to factor out just one of the 4s. And then I'd have -3 to the n minus 1 over 4 to the n minus 1. And notice if you multiplied that 4 back in, you would get the power of n again. So now you have this. And the great thing about having it looking like that is if you have two numbers raised to the same power, it's the same thing as having that fraction raised to that power all at once, if you get what I mean. And you can distribute it back just like that. And now you can see what the things are supposed to be, right? Like you have this a sitting here, and then you have this r right here. That's the value, the fixed r that's getting raised to the n minus 1 power. So this time my r is -3/4. Absolute value of that is certainly less than 1. So we know this is a convergent geometric series. Now I'm going to use my other formula. So the sum of this right here, it's equal to, this is the one I do in my head. Even if I write this in class, just know that I'm actually thinking this formula always. I say first term 1 minus r. I say that in my head when I do these problems. So it's first term over 1 minus r. The first term is you plug in the first index that applies. This time it's a 1. It doesn't have to be a 1, but it says 1 here. You plug in 1 and you figure out what you get. So if you plug in 1, you get something to the 0 power is 1 times a 4th. The first term is a 4th. Because I plugged in 1 and overall I got a 1/4. 1 minus my r value is this that's getting raised to the n minus 1, so that's -3/4. And just notice you get a double negative this time. So this is 1/4 divided by, if you add these two together, you get 7/4. And the 4 and 4 cancel, and you just get 1/7. So this infinite geometric sequence converges to 1/7. OK, in the next part of this video, I'm going to show you a test that will show you when a series diverges when you don't have an actual sum, in some cases. And then I'm also going to show you one other type of series that we can find the sum of. And partial fractions will come back for that. So yeah. Until then, I will see you in just a second.